All right, so we are welcome back to class again this morning as we continue in our study on hydrolysis of ions. Let me first ask, I hope you all slept well, and I hope you find time to go through what you were taught yesterday. Like I always tell my students, this is a university now. Please, whatever you are being taught every day, don't let it lie down until you have gone through it before you go to bed every blessed day. That's the only way you can retain most of the knowledge stuff that you've been taught. All right. So today we continue from where we stopped yesterday. I think I'm coming, please. Let me just give me some few minutes. All right. So we have been able to establish that there is a relationship between the acid dissociation constant and the hydrolysis constant of the corresponding ion of the conjugate base that is formed from it. Similarly, we also established a relationship, an inverse proportional relationship between the base dissociation constant and the hydrolysis of the conjugate acid. All right. We've done that yesterday with all carefulness. Some students complaining that they do not understand, want to appreciate the university for making it possible for you to be able to access the video of the lecture. So all you need to do is go on YouTube, go to Faculty of Computing, and you will see TELEPRESENCE. From TELEPRESENCE, you see this series of courses that are on TELEPRESENCE. So you can click on Chemistry 101, and of course you can access any of the videos at your own convenient time in the comfort of your room or wherever you are. You can always access it so that you can go through what have been taught previously. All right, so let's commend the university for making this available for us as students. But I haven't said that, with all that we did yesterday, so today, can we see how we can apply the concepts taught yesterday by looking at some of the questions here. All right, so the first question here says you have to calculate the pH and the extent or percent hydrolysis occurring in the following. You have 0.100 molar sodium acetate. Given that the acid dissociation constant for acetic acid is 1.8 to the power of -5. Now let's quickly take our time to go through that. So I'll go to the next slide. All right. So what are we given? 0.1 molar sodium acetate, 1.8 for the acid dissociation constant. So let's go through that together. All right, so so we have sodium acetate, which I will represent as NaAC. All right, because it's a sodium salt, it will give us sodium ion plus acetate ion. All right, acetate ion is simply CH3COO minus. That's what we call acetate ion. What concentration of it are we given? All right, we're given 0.1 molar. All right, so since it's a sodium salt, so when we have 0.10 molar of this, a sodium salt will ionize completely in solution. We are saying before ionization, there'll be nothing here, but after ionization, all of this will have gone, and of course, we're going to have 0.10 of this, and of course, 0.10 of this. Our interest is in this, all right, because this is formed from acetic acid. So we can write For the hydrolysis of acetate ion, let me now write it this way, acetate ion. For the hydrolysis of acetate ion, so we're going to have now acetate ion is now a base because it's the conjugate base of an acid. So it pick up proton from water to become acetic acid plus OH minus. Okay, it is the presence of this OH minus now that makes the solution basic. So, so we have started. So our initial concentration, we have 0.10 of this. Of course, there won't be anything here. There won't be anything here. The changes that will have occurred at equilibrium, by the time X of this is gone, X of this will have been formed. X of this will have been formed. And of course, X of this also will have been formed. All right. Such that what is left at equilibrium, therefore, will simply be equals to 0.10 minus X. And of course, this will be, excuse me, please, this will be X. And of course, this will be X. All right, so that is what we have. Now, the equilibrium expression for this reaction, the equilibrium expression is hydrolysis. So let me put KH on top of this arrow so that we can write that KH for this acetate ion will be equals to the acetic acid form, CH3COOH, the OH minus form, and of course, the undissociated acetate ion. If we substitute for that, according to what we have on the ICE table, we have X over 0.10 minus X. All right. Now, recall that KH is equals to KW over KA, and that will be equals to 1 to the power of minus 14 over 1.8 to the power of minus 5. All right, let's find out what that will give us. Let's bring out our calculator. If you are there with a calculator, please bring it out. Get this for me. I want to see your comment, what you're able to do on the, as I'm monitoring what you are doing, so you can be doing it as I'm doing too. So we are looking at 1 to the power of minus 4. My 1 to the power of minus 14, I beg your pardon, divided by 1.8 to the power of minus 5. 1 exponential minus 14 divided by 1.8 exponential minus 5. And that should give us 5.56. That'll give us 5.56 to the power of minus 10. 5.56 to the power of minus 10. Okay, it's apparent here that the value of the equilibrium constant is extremely very small. So that would make our assumption justifiable. So we assume that 0.10, oh sorry, assume that X is far less than 0.10. It will mean, therefore, that 0.10 minus X will be approximately equals to 0.10. Okay? If that assumption is right, and of course it's going to be right, because what will make it right is the fact that this value is extremely very small, as you can see. All right, so let's proceed. So we can write, therefore, permit me to write here now for space. So we can write that KH will be equals to x squared over 0.1. That is the KH that we have obtained, 5.56 to the power of minus 10 will be equals to x squared over 0.1. And that is x squared now will be equals, when you cross multiply, you get 5.56 to the power of minus 11, such that x, which of course is equals to x, which is equals to hydrogen ion concentration, will be the square root of this. So let's find out what the square root of 5.56 to the power minus 11 is. Okay. All right. Thank you. All right. So trying to find the square roots of all this. And there we have 7.45 to the power of minus 6. So we have 7.45 to the power of minus 6. Now, that is the hydroxide ion concentration in this solution. Now let's make progress. Okay, that is what I've just explained here now. As you can see, that's what is being displayed for you. I mean, I've just solved it now. It's something I've just done now. So we have 7.48 to the power of 7.45 to the power of minus 6. Okay, so if that is true, and of course it is, then we can proceed and say that so that's the OH concentration. All right. Now that we know what 7.45, 7.48, I guess approximation error and there will be responsible for this little difference. But then we really shouldn't bother ourselves about the little difference. Is the concept that we should actually be get ourselves worried about to understand it. All right. So I want to say that. So we can then say this is the OH concentration as obtained. So the POH, of course, is minus log to base 10 of OH. So minus log to base 10 of 7.48 to the power minus 6 will give us 5.13. Okay? And of course, the question asks us to calculate pH, and we all know that pH is pH plus POH is equal to 14, such that pH will be equal to 14 minus POH. Having obtained the POH to be equal to 5.13, then the pH becomes 14 minus 5.13, which is 8.87, which is 8.87. So you can see we have been able to calculate the pH. The question asks us to calculate the percent hydrolysis. Of course, the percent hydrolysis will simply be equals to X. That's the amount of acetic ion that have hydrolyzed divided by 0.1, which is the concentration of acetic ion in solution. So we can say the percent hydrolysis. So we can say percent hydrolysis will be equals to the amount that have hydrolyzed. That is 7.48 to the power of minus 6 divided by 0.10 times 100. And if that is done with all carefulness, we'll find out that this will be equals to 7.48 to the power of minus 3%. How you can see, it's extremely, and I mean extremely, extremely very small. Okay, and I think that's convey to us that the extent of hydrolysis is very, very negligible. Okay, I've just done that now. That's it. Now let's look at for the ammonium chloride, just as we did for the acetate ion. Now we know that ammonium chloride, all ammonium salts, because some students may be wondering, how do we get this? So don't let us jump. Let's just write. We know that ammonium chloride, all sorts of ammonium ion, we ionize completely to give ammonium ion plus chloride ion. All right. So we are given 0.2 ammonium chloride. So by the time it ionizes, all of this will have gone, and you're going to have 0.20 molar of this and 0.20 molar of this. Now that we know the amount of ammonium ion in solution, ammonium haven't come from ammonia. Don't forget, ammonium ion is formed from ammonia. Now, ammonia is a weak base. Okay, so this will be a conjugate acid of ammonia. Ammonium ion will be a conjugate acid of ammonia, and of course, it will undergo hydrolysis according to this equation here. And so, without wasting time going through the IC table as we've done before, because it's essentially the same thing, I've just jumped at that step. Of course, it's not because it's because it's very easy to understand now. So we have at equilibrium, ammonium is 0.2 minus X, and of course, ammonia will be X, and H3O will be X, such that the hydrolysis constant, because what we have here, please let me write this. Like I said, is because the software could not see math type. I use math type to type the equations. All right, so this is what we actually have there. So this is KH on top, and then we have ammonia plus H3O plus. Okay, so this this one that you could not see very well is what I've just represented here. All right, so I've once done that, so we can say that KH will be equals to ammonia multiplied by hydrozonium ion concentration divided by ammonium ion, which of course will be equals to KW over KB, right? And that we get to be equals to, just like we did previously, that's also 5.6, because the for KB is also 1.8 to the power of minus 5. You know, just like we have for, it's just a coincidence that they are the same, okay? And so we have X squared over 0.2 minus X. Since this is very small, as in extremely small, it can be assumed that X is far, far less than 0.2, such that 0.2 minus X is just 0.2, okay? Just as we did previously, you get our X to be equals to 1.06 to the power of minus 5. Okay, so it's a very simple and straightforward idea. And so from there, we know what the questions ask us to actually calculate pH anyway. And so since we know hydroxonium ion concentration to be equals to 1.06 to the power of minus 5, it becomes very easy to calculate the pH, since the pH is minus log to base 10 of hydrogen ion concentration, and that got to be equals to 4.98. Then, of course, the percent hydrolysis, you can see that very, very small, 5.30 to the power of minus 3%. Okay, so with these two examples to illustrate the concept of hydrolysis, I want to strongly believe that if you see any question on such concept, you'll be able to provide answer to it. Now, to be sure that you do, have these practice questions here for you. Sodium formate. Sodium formate is formed from the combination of sodium hydroxide and formic acid. Formic acid is what we call metanoic acid, HCOOH. HCOOH. All right, that's so. So you have formic ion. You should be able to answer this just like we did for sodium acetate. The same thing go for potassium propionate. Okay, that is formed from propionic acid and of course potassium hydroxide. Okay, you should be able to do that also with relative ease. Then this one is a base, ethyl ammonium chloride. You know, that is from ethylamine and a strong acid. Ethylamine is a weak base. HCl is a strong acid, that's hydrochloric acid. So when the two combine together, just like you have ammonia and HCl to give ammonium chloride, so you also have ethylamine combining with hydrochloric acid to give ethyl ammonium chloride. Okay, so the ethyl ammonium ion will then undergo hydrolysis. And I'm sure if you apply what we've done previously to these three questions, you should be home and dry. Right? Are we okay with that? Or while you are looking at the question carefully, let's take the first code for attendance for today. The first code for attendance today, I'm going to write it here. We have BS2QC. BS2QC is written on the screen for everybody to log in now for the first code of the attendance. And let me see what your response is so far. Yes, so please be filling the attendance. I'm trying to see. Okay, somebody says, sir, is the KB constant? Of course, it's a constant. That's what we call it. Base dissociation constant. It's constant at a particular temperature. Constant at a particular temperature. American boy, you need to up your game. This question go far. You make me laugh. All right, please, just take your time to go through it at when you are free. That's why I said let's appreciate the university for making it available on YouTube, so you can take your time. Don't be in a hurry. You might not be able to follow everything within 1 hour of lecture, but at your own convenience time, just sit down and go through it again and again. Then I'm sure you will understand what is being taught. All right? All right, well done, everybody. All right, so we're still on chemical equilibrium. Equilibrium in solution, that's what we're doing. We are still going to be on equilibrium till next week, Wednesday. All right, till next week, Wednesday. That's on the 24th, the 24th of this month. All right. Okay, so thank you very much. Let's proceed. Okay. One of the most important applications of the acid-base equilibrium is in the preparation of what is known as buffer solution. I want to encourage my students, especially those of you in biological sciences. You're going to do a lot of preparation of enzyme and stuff like that. You know, my students in microbiology, my students in Faculty of Agric, my students in biochemistry, maybe chemical engineering. You're going to need a lot of preparation of solution that you want the pH the pH to remain fairly constant for a very long period of time. Okay, and so as to keep the pH constant, then you need to know the concept of buffer. Okay, for example, the human blood, we eat all manner of food. You eat oranges, you get ascorbic acid, citric acid, you eat meat, you eat egg, so you get proteins, and from proteins, you get acid, you get base. Protein is, of course, made up of amino acid, amino, base, acid. You can see that. So we eat all manner of things, and yet, the pH of the blood remain essentially constant without any change. Should there be any change in the pH of your blood, then of course something is wrong with your erupt. An imbalance has taken place. That's one of the very important practical application of this concept. It then implies that your blood, the blood in our system, God is an amazing God. We should every day appreciate God when we have this kind of knowledge. Appreciate God because the blood in your system is a buffer solution. Irrespective of the junks that we consume, the blood pH remain essentially the same. If there's any alteration, any slight change, then of course, hospital will be the last place that the individual will go. So let's give thanks to God every day. Now, having said that, what constitutes what's a buffer in the first instance? Just like we use blood now, you eat all manner of things, acidic, basic, and yet the blood pH remain constant. It means that your blood is a buffer system that resists a change in its pH. The blood is a system, a fluid that resists a change in its pH when some amount of acid or base or any other electrolyte is added to it. That's what we call a buffer solution. So generally, a buffer solution is one that resists change in its pH despite the addition of a small amount of an acid, a base, or any other electrolyte. Okay, then what makes a buffer? The composition of a buffer. Buffer, we have two types of buffer. We have acid buffer and we have base buffer. For an acid buffer is a mixture of a weak acid and a salt of that weak acid. A mixture of a weak acid and a salt of that weak acid. For example, acetic acid and sodium acetate. Acetic acid, weak acid. Sodium acetate is a source of acetic acid. The mixture of the two will constitute a buffer. We also have what we call a base buffer. A base buffer is combined of is composed of a weak base and a salt of that base. A weak base and a salt of that base. For example, ammonia is a weak base and ammonium chloride is a salt of ammonia. So when you have a mixture of ammonia and ammonium chloride, you have what we call a base buffer. Now let's take, to illustrate this concept, American boy, I want you to please listen because you are saying that this calculation is too far. Maybe this one's going to be farther. So I want you to prepare your mind to enjoy the how far this question will take you. All right, so the question says, consider a mixture of 0.10 molar acetic acid, which we represent as HAC, and 0.10 molar sodium acetate. Now let's see what happened in the mixture of the two. Okay, so we have acetic acid. The acetic acid, being a weak acid, we undergo this. Let me rewrite this better. What you have there is an equilibrium sign with Ka on top to indicate weak acid. All right, so this is what we have there. So for acetic acid, in solution with hydrogen ion and acetate ion, if X of acetic acid had been used up or ionized or dissociated, then X of hydrogen will have been formed and X of acetate ion also formed, such that at equilibrium, you are left with 0.1 minus X of acetic acid, and of course we have X of hydrogen and X of acetate ion. However, for sodium acetate, because it's a sodium salt, represented, that's why we represent that expression by a single arrow. It's a complete ionization, such that by the time 0.1 molar of sodium acetate are ionized, you have only in solution of that solution 0.1 molar sodium ion and 0.1 molar acetate ion. Now, what happened here? Sodium acetate is a very strong electrolyte and is an annexer, so it ionizes completely, like I've said. Now, if there is only acetic acid initially, we know the acid dissociation of acetic acid is 1.8 to the power of -5. So it's a weak acid by virtue of that value of its dissociation constant. It's an extremely weak acid. All right, so we are saying that suppose there is no sodium acetate in solution, suppose only acetic acid, apparently the amount of acetate ion that will have been in solution will be very small compared to the initial amount of acetic acid. Okay, now we are now introducing acetate ion from sodium acetate again. My apology, I ought to have taught us factors affecting position of equilibrium before now. My apology for that. I'll come back to it. But of course, I'm sure you were taught in secondary school, Lee-Chateli's principle. And what Lee-Chateli's principle is saying is that when a stress is imposed on a system at equilibrium, the equilibrium will adjust itself in such a way as to annul the effect of the imposed stress. When a stress is imposed on a system at equilibrium, when we say stress imposed, that is, you are changing some factor. For example, you can change concentration, you can change pressure, you can change volume, so these are the stress you have imposed to alter the equilibrium position. The only way the system will adjust itself, the system will adjust in a way to remove the effect of the imposed stress. Now, listen up, please. Listen up, please. American boys and others, please listen to me. We know from acetic acid, the amount of acetate ion is very small. Now, from sodium acetate, we are now having 0.1 molar acetate ion. So what happened to this equilibrium, because of the presence of this, is to remove the acetate ion. So the equilibrium will shift to the left. Originally, the amount is very small. Now, when it's now being shifted to the left again, it becomes smaller than it would have been normally. All right, such that we can say, to a very close approximation, that any acetate ion in this solution, any acetate ion this nature, will be exclusively from the sodium salt and not from the acid, because the one from sodium salt is 0.1, the one from acetic acid is maybe usually is 3.33% hydrolysis. So if you have 0.1 and you're looking at 3.33% of 0.1, apparently you're going to get something like 0.003 or 0.0003. So that's what will have come from here, from this equilibrium. Now we are now introducing 0.1. The presence of this will reduce this further. And of course, you can see when you compare 0.1 with this, it's going to be far, far greater than this. All right, such that whatever is in solution will be exclusively from the salt. I hope that is clear. That's what I'm trying to explain here. All right, I haven't explained that. All right, so for the dissociation of the acid, of course, this is the acid. Let me write again. HAC, dissociating to give H plus AC minus. So we can write that Ka for this, of course, will be equals to H plus AC minus over HAC. All right. Now the hydrogen atom concentration, make it the subject of the expression. will simply be equals to, sorry, excuse me, sir. I'm having an issue here. Automatic restart ratio 2 for important. Okay, now if you take minus log to base 10 of both sides of this expression, you have minus log to base 10 of H plus will be equals to minus log to base 10 of Ka plus minus 10 minus, sorry, log to base 10 of HAC over AC minus. Okay. This, of course, we know is pH. So we can write this as pH will be equals to, this we know as pKa. So we write pKa. Now, this is minus plus, this is minus. But if I flip this so that AC will go up and HAC will come down, this will become plus. So I can have plus log to base 10 of AC minus over HAC. HAC. Okay. Now, the AC minus is the acetate ion in solution. And we have established that the acetate ion from solution will be exclusively from the sodium acetate and not from the acid itself, since the one from the acid is very, very small. So it can then mean that the pH will be equals to pKa plus log to base 10 of the concentration of the salt over the concentration of the acid. This equation here is the equation we use to calculate the pH of a buffer solution. This equation is known as Anderson-Hasselbalch equation. Anderson-Hasselbalch equation. That's what I've just written here is already here for you. I just wrote it so that you can feel how we derive it, nothing more. Okay, and so that is what we have here. This equation is very, very important. Now, if you do not know anything, please know this equation. All right, please know that pH is equal to pKa plus log to base 10 of the ratio of salt and acid concentration. This is called Anderson-Hasselbalch equation. Okay. The same argument goes for a base buffer. Okay. We have a mixture of ammonia and ammonium chloride. The ammonia will not ionize appreciably because it's a weak base. Okay. Why the ammonium chloride will ionize completely in solutions? The summary is that any ammonium salt that is present in solution will be exclusively from the salt and not from the base. since the amount from the base is very, very small. Okay, so using the same argument as we did in the previous slide, we write for this expression, the base dissociation constant is this. We make OH the subject of the expression, and of course, we have this equation. If we take log of both sides, take logarithm of both sides, you're going to have POH is equal to PKB plus log of, now we flip this over, ammonium ion over ammonia, so that it can be positive. Okay, or no, otherwise it will be negative. But because we have changed the position, we flip it over, so we have ammonium over ammonia. Like I said, the ammonium ion is excluded from ammonium chloride, so we can write there, therefore the POH for a base buffer will be equal to pKa plus log to base 10 of salt over base. Now, once we know the POH, it becomes easy to know the pH. Okay, so you want to know the pH for this, you just simply say, for this solution now, pH equals to 14 minus all this. 14 minus all this. That's what the pH will be. That's another variant of the Anderson-Esselbach equation for base buffer. All right. To illustrate all this, before we start that, can we take our second code, attendance code for today? The second attendance code for today is 4L8 D7. 4L8 D7. Thank you. Please log in to the attendance now and put in the second attendance code. Thank you. Now, if while doing that, let's now see what is what we can get from this question. Let me hear you. Let me see. Let me feel your thinking as far as this class is concerned. Okay, somebody's asking question. I say for L as in love. L as in love, not M. I didn't say M, please. Ajayi Daniel is 4L8 D7. All right. Doctor's blessing. You can't see anything. Why? Why are you sure you can't see anything? Any other person not being able to see? We are only seeing your face, sir. Yes, you're only going to see my face now. But while the slide is mounted, you should be able to see somebody saying, sir, we don't see anything. It's true we are seeing, sir. It's not the slide. Okay. We have not been seeing slide for like 7 to 8 minutes. Okay. All right, it's all right. We will work on that. Let's see now. Can you see the slide now? If you can see the slide now, please let me know. I just mounted the slide. I have here, I calculate the pH of a buffer solution consisting of 0.50 molar HClO. That's a weak acid. Okay, HClO, hypochlorous chloride acid, HClO. All right. I don't know whether you are seeing it. Okay, let me check your comments now. Please, if you are seeing, let me know. Okay, they say no. Still not seeing it, sir. Okay, please, sir. They're not seeing the slide. They're only seeing my face. Is that what this is? Yeah. That's the comments, everyone. Yeah, we see just your face. And I don't want to see my face. I want to see what I'm teaching you. I'm sure. I didn't cancel. I canceled that button. Okay, can you see me? Can you see the slide now? Please let me know before I continue so that we don't waste time. I still about 14 minutes. I want to be sure that you're seeing the slide and not my face. This one say you're not seeing my by now you should see the slide now. That's not true. It's blank, sir. No. Yes, you. Yes, you. Mm. Mm. All right. I hope by now you can see the slide now. All right. If you can still not see the slide, let me hear from you, but I'm sure you'll be able to see it now. Yeah. Okay. Okay. Can you hear me now also? All right. Thank you. All right. Thank you very much. You can see it now. Thank you very much. You can see and hear. All right. Thank you. Thank you. I appreciate that. Now let's quickly go through this because time is fast spent. All right. So we are looking at this question. Say calculate the pH of a buffer solution consisting of 0.50 molar HClO. The acid dissociation constant is 2.9 to the power of minus 8. It's a weak acid indeed. And 0.60 molar NaClO. Now, calculate the pH again after adding 0.020 mole of solid sodium hydroxide to 1 liter of the buffer solution in part A. Then, of course, what happens if you add 30.0 ml of 1.5 molar HCl to 0.50 liter of the buffer solution in part A? Now, at this point, I would like you to please listen and listen well. Okay. Now, like we have established in our previous class, in our previous slide rather, the pH of any buffer solution is given by the Anderson-Hasselbalch equation that say pH is equals to pKa plus log to base 10 of salt concentration over acid concentration. In this wise, the salt is NaClO and the concentration is 0.60 molar. The acid is HClO and the concentration is 0.50 molar. And of course, the Ka for the acid is 2.9 to the power of minus 8. Substituting for this value in the Anderson-Hasselbalch equation, we have that the pH will be equals to minus log to base 10 of Ka, because that's what pKa stands for, minus log to base 10 of 2.9 to the power of minus 8, please, not plus 8. Please, what we have is 2.9, please, 2.9 to the power of minus 8. That's a typographical error here. Okay, it's minus 8. All right, plus log to base 10 of NaClO, because that's a salt, and HClO is the acid. A careful slotting of the value will give you a pH of 7.62. If you carefully do that, you get a pH of 7.62. I want to please bring out your calculator confirm that this is correct. It's always good for you to be actively involved in the class by, punching the calculator to be sure that you're understanding what is being taught. All right. So if that is clear, and I want to believe it should be, where we will have issue is in the B and the C part. And that's where I want to give me your rapt attention. Now, what happened if you add 0.02 mole of solid sodium hydroxide to 1 liter of the solution? It means that you have added 0.02 sodium ion and 0.02 hydroxide ion. The sodium hydroxide will definitely, being a strong base, react with HClO. Let's write that so we know what happened there. So this one will happen. Let me delete OSH. Okay, don't worry. Okay, I want to just delete. Okay, I can just delete on the. Okay. Okay, let me just. It doesn't matter. Here is Okay. All right. So this what happened here. Like I said, this is -8, please. All right. So what happened if you add? So we are going to have the sodium hydroxide here will react with the acid here. So we're going to have HClO reacting with sodium hydroxide. And that will give us this acid-base reaction. That will give us NaClO plus H2O. So in that wise, we have 0.5 of this. We have 0.02 of this. Now, according to stoichiometry of the reaction, this is the limiting reagent because this is 1 to 1. So the question is how much of this will have been formed. And since this is the limiting reagent, what we form here will also be 0.02 molar. And what will now be left here will be 0.5 minus 0.02, which of course will be equals to 0.48. So in solution, you're going to have 0.48 of this, and you're going to have additional 0.02 of this. Now, this additional 0.02 will now combine with this to give us 0.62. Okay, so that in the solution, finally, the amount of NaClO will be what initially you have, 0.60, and what will have been formed from this reaction plus 0.02, and that's 0.62. All right, and this acid now, because some of it have been used now, this acid, some of them have been used to react with sodium hydroxide, what will be left of it is 0.48. So if you now use your Anderson-Hasselbalch equation again, okay, so the summary is now that in solution, we have NaClO, which will be equals to 0.60 plus 0.02 molar, which is 0.62 molar. And the acid now, HClO, please, HClO will then be equals to 0.50 of it minus what have been used, 0.02. Okay, and that will be equals to 0.48. molar. So now you have the new concentration now. The pH now becomes pKa plus log to base 10 of the ratio of sodium ClO, which is the salt, over HClO, which is the acid. And that becomes the pKa, that's minus log to base 10 of the Ka, which is 2.9 to the power of minus 8, 2.9 to the power of minus 8, plus log to base 10 of 0.62 over 0.48. And let's see what value we obtain from that. Let's quickly do that before we now take our last code. Let's do that together now. So we're going to have 2.9 exponential minus 8 okay. So we're going to have here 7.54, which we have before, plus 0.62 divided by 0.48. And of course, we're going to have 0.11. And so you're going to get a new value of 7.65. 7.65. Compare that to what you obtained previously. Compare that, you have 7.62 here, and here you have it 7.65. You can see the change is very, very minimal. Okay, so we'll continue from there on Friday. There won't be class tomorrow. We'll continue from there on Friday by 9 a.m. And the last code for today's class, the last code for today's attendance is 8T SDF. 8TSDF. Please, our time is up now. So we are given just the next 2 minutes to please log into the attendance. And oh, this is a very good question. This one is saying, who is enjoying the class? Yes, 0.6 is in the question. You are right. Elizabeth Olawumi Afolayan, 0.6 is in the question. That is the, how do we get the 0.6? Okay, somebody is responding to that. 0.6 molar. That's what we're given, okay, as the concentration of NaClO. Okay, thank you very much, Elizabeth, for responding to the class. William Debra, who is enjoying the class. If you're not enjoying it, okay, don't worry. We'll see what we can do to improve on the delivery next time. But just make sure that you take your time to go through it again. I can go back to the YouTube and listen to the lecture so they can enjoy it. Okay, thank you very much, everybody. I'll see you again, God's willing, on Friday by 9 a.m. Thank you very much. Have a great day ahead of you. the stream current bit rate is lower. Warning. ATHDF, thank you. Ọmọdé ìṣá Adéwálé Tìmílẹ́yìn. You're not following the class. That's why you couldn't get the code. 8TS not DL, DF. Someone say, is it M? How can it be M? I said 8TSDF. 8 Titilayo, Shola, Dayo, Funke. 8 Titilayo, Shola, Dayo, Funke. Where did I see the 0.48? Yeah. The 0.48 was obtained when you have the acid initially at 0.5, but you have now added sodium hydroxide that is 0.02. The sodium hydroxide will react with the acid. Okay, but not all the acid will react. What is left of the acid will be 0.5 minus 0.02, and that's where you get the 0.48. Please, who said that now? Ayomide 14H. Sorry. Yes, the B2 is silver. All right, that's it. I hope you get that now. Yeah, I'm there with you. What response for everything? Go ahead and